In this video, we'll introduce hydrostatic pressure and force. Think of hydrostatic pressure as how hard a fluid pushes on a specific part of an object. Force is then the total push on the object, not just on a specific part, but the total push. The pressure exerted on a submerged object by a fluid changes with depth, but is independent of the volume of the fluid. Think about a goldfish. Let's call him Gil. Brownie points if you actually get that random reference. Let me know in the comments. Just don't make fun of my horrible drawing skills. Let's say Gil is 2 feet below the surface of the liquid, the water. It doesn't matter if he's in an aquarium or in the lake. The pressure is still the same regardless of the volume. At any point in the fluid, the pressure is the same in all directions. So the pressure around his eyes is the same as the pressure right here at his tail. We can use this idea to say that pressure in any direction at a depth of d in a fluid with weight density delta is given by this equation. Pressure equals delta times d. Delta, we will typically be using the weight density of water, which is 62.5 pounds per cubic foot, unless we're otherwise told. Now, this is not always a straightforward problem because pressure changes, it's not constant. As you go deeper, the pressure increases. We'll see this used in examples where we have a plate submerged or partially submerged underwater, or looking at the side wall of a dam. A vertical plate is submerged in water and has the indicated shape. Explain how to approximate the hydrostatic force against one side of the plate by a Riemann sum. Then express the force as an integral and evaluate it. We'll approach this similar to how we initially approached integration and finding area under the curve. Recall we would split that area into n different rectangles. Similarly, we'll split this plate into n different slices. Let's say the thickness of that slice is delta x. We'll also need to have some kind of orientation. So let's label an axis here. Let's say that the top of the water is at 0. And if the plate is 3 feet down, then this will be 3. And let's say that slice is at an arbitrary x sub I. Then the bottom of the plate would be at 11 since it's 8 feet long. Now focusing on that strip. The area of that strip is base times height. The base being 2, the height of that strip is delta x. Then the pressure on that strip will be the weight density of water, delta x sub I, where delta is the weight density of water, roughly 62.5 pounds per cubic foot. And x sub I is the depth. Keep in mind pressure increases as depth increases, so that's going to change as we go further down. The force on the strip now is then delta x sub I times the area of the strip to delta x. Keep in mind that is the force on just that strip. We want to find the total force. The limit as n goes to infinity of the sum from I equals 1 to n of delta x sub I times 2 delta x. And now using our integral notation, the force will be the integral from, we're starting at 3 and going to 11. Delta x times 2 dx. We can pull 2 delta out of the integral since that's just a constant. We now have 2 delta. We'll integrate. The integral of x is 1/2 x squared, and we are evaluating from 3 to 11. Notice the 2 and the 1/2 will just multiply to 1. So we have delta times 11 squared minus 3 squared. That is delta times 121 minus 9, which is delta times 112. And now if we use the approximation for delta, the weight density of water, 62.5 times 112, we'll get roughly 7,000 pounds. In this example, we will again be looking at hydrostatic force on a plate. We'll start by labeling an axis. Let's say the top of that plate is at 0, the top of the water is then at 1, and the bottom of the plate is at 3. And we'll focus on an arbitrary strip in that plate. Let's say it's at a depth of x sub I. The height of that strip is again delta x, like last time. Focusing on that strip, we need to first find its area. The area of the strip, that rectangular strip, is base times height. But the base of that strip is changing depending on where it is on the trapezoid. So it's not quite as simple as it was in the previous example. We'll need a way to label the length of this strip according to its depth, x sub I. To do that, we'll use a little bit of geometry. Let's break this shape up into 3 different parts. We'll have a square in the middle and 2 triangles. Let's focus on those 2 triangles, mainly this one over here. Let's focus on this triangle. The height we know is 3, and the base is going to be 2. If this is a square, this is 4, and then the 2 bases are 2. Let's then also focus on this smaller triangle. Its height here is x sub I. So the height of that triangle we'll call x sub I. And the base we don't know. Let's give it a new variable. Let's call it just w sub I. Notice we have 2 right triangles and they are similar. So let's set up a proportion. 3 is to 2. The height is to base as x is to w. X sub I is to w sub I. And we're trying to find w. So we'll cross multiply. 3 w sub I equals 2 x sub I. And then solving for w sub I is 2/3 x sub I. So notice we just found w sub I. It is the base of the red rectangle. So this piece here, w sub I. We can now find the area of this red strip. The base is 4 plus 2 W sub I. That's the base of that strip, and its height is delta x. We now have 4 plus 2 times W sub I, we said, is 2/3 x sub I. We now have 4 plus 4/3 x sub I times delta x. That is the area of that strip. Now the pressure on that strip, delta, the weight density of water, times the depth. And since the top of the plate is 1 foot above the water, then the depth is going to be x sub I minus 1. Now the force on the strip will be delta x sub I minus 1 times the area of that strip, 4 plus 4/3 x sub I delta x. Now we can find the total force using our summation notation. We have the limit as n approaches infinity, sum I equals 1 to n of delta x sub I minus 1 times 4 plus 4/3 x sub I delta x. Then using the integral notation, we have the integral from 1 to 3 delta x minus 1 times 4 plus 4/3 x dx. From here we can pull the delta out of the integral. That's just a constant, and we'll distribute to clean this up. We get 4x plus 4/3 x squared minus 4 minus 4/3 x dx. Simplifying a little bit more, we have the integral from 1 to 3. So we get 4/3 x squared. Combining like terms, 4x minus 4/3 x will give us 8/3 x. Then we'll just bring down the minus 4 and the dx. At this point, we can start the integration. We get 4/9 x cubed plus 4/3 x squared minus 4x. And we are evaluating from 1 to 3. Now plugging in those limits of integration. 4/9 times 3 cubed plus 4/3 times 3 squared minus 4 times 3 minus, plug in the lower limit, 4/9 times 1 cubed plus 4/3 times 1 squared minus 4 times 1. We'll now have delta times, I'll let you verify this in a calculator, we have 128 divided by 9. And again, delta is the weight density of water, which is roughly 62.5. We'll multiply that times the 128 divided by 9, and we get roughly 889 pounds.